Hello everyone, in this video we're going to continue with polar coordinates, but now we're going to talk about from the point of view of parametric equations. So before we talk about parametric equations to a way to describe a curve, where we describe the coordinate x and y as something in terms of a parameter that helps me describe how a curve is described. In terms of polar coordinates, we pretty much do the same thing, but in here, the type of equations that we're having are from the form r equals f of theta. So, of course, because our curves are now in terms of polar coordinates. Or, in a more general fashion, we can consider that curve as a big F of r and theta equals 0. And that's going to consist of all the points that has at least one polar representation that satisfies that equation. Now, one of the initial type of coordinates that we can think in this way is if we represent something like the polar equation r equals 2. Notice that what is this saying? This is saying is all the points that has distance 2 from the pole. So because we're thinking in that way, we take all the points r theta with r equals 2, regardless of the angle. And so, as you can probably guess, this is going to produce a circle of radius 2. So, also all the points that have distance 2 out of the pole O. If you replace the equation for r equals a, this is going to represent a circle with center in O and radius a. As you can see here, we have some examples. R equals 1/2, r equals 1, r equals 2, which was our initial questions, and r equals 4. So they're all circles, but this is the most simple equation that we can have. You only have r equals something. Now let's think of something that is a relationship r equals f of theta. And so we have r equals 1 plus sine of theta. In this case, the first thing that we can do is analyze how things are going to move. So we can take r equals sine of theta in Cartesian coordinates, like a plane, and just see how it behaves. How it behaves when I give values of theta. So I'm going to see what happens with r once that I start giving values of theta. So initially, if I go from 0 to pi half, notice that I can see that r is changing from going to 1 up to 2. This is something that we can also see on the left side picture, where we start in the polar plane. And so we initially, when r is equals 0, then we start with a distance theta equals 0. Sorry, we start with a distance r equals 1, and then the distances start increasing up to 2 when we arrive to pi half. Now, if we continue going from, let's say, pi half to pi, then notice that again we're going to have a decreasing behavior from 2 to 1. If theta increases from pi to 3 pi half, then we're going to have again that it decreases from 1 to 0. And finally, as theta increases from 3 pi half to 2 pi, then it's going to increase from 0 to 1. So all the behavior that it's doing is something like this. First, when we're going from 0 to pi half, here we have in the second picture the blue sketch of what it's doing. Then when we're going from 0 to pi, you see the red line here that is covering this piece, and it is again going from now 2 to 1. The third picture shows how it goes now when we're going from pi to 3 pi half. It's going to decrease from 1 to 0, and it does this behavior with the r. And finally, when theta is increasing from 3 pi half to 2 pi, then it does this last little bit when it's increasing from 0 to 1. Notice that the behavior that it has depends on the quadrant. Remember that each quadrant here is represented in angles. So the first quadrant is 0 to pi half, the second quadrant is pi half to pi, the third quadrant is pi to 3 pi half, and the fourth quadrant is 3 pi half to 2 pi. And what we're drawing is the behavior of the curve in each of those. This curve is what we call the cardioid. Okay? Now, When we're sketching polar coordinates, sometimes it's going to be useful to take advantage of symmetry. So if we have a polar equation isn't changed when we replace theta by minus theta, then we can say that is symmetric with respect to the polar axis, like in figure A here. You can see that it doesn't matter if you're taking r theta or r minus theta, it's just going to have the same behavior. Whatever we have with respect to the polar axis, you have a reflection below the polar axis. If the equation isn't changed when you replace r by minus r, or theta by theta plus pi, then we can think that the curve is symmetric with respect to the pole. So that's why you see this behavior in figure B when the figure, whatever we have in the first quadrant is reflected the same way on the fourth quadrant. This is some symmetry with respect to the pole. Last, if the equation isn't changed when we replace theta by pi minus theta, then the curve is going to be symmetric through the line that goes through the pole. So like the equivalent of the y-axis, but on the polar coordinates. And so you can see here that the left and the right are symmetric. They have the same behavior. So we have this type of behavior when we're sketching, then of course we're going to have a case of symmetry with respect to the pole, or respect to the vertical line. Now, graphing polar curves is sometimes something that is going to be very complicated to do by hand. This is definitely not something easy to do by hand. So it's best sometimes to use technology, especially because since it's useful to do it by hand, some of them are very complex. So for example, we have this example here, r equals sine cube of 2.5 theta plus cosine cube of 2.5 theta, or r equals sine square of 3 theta over 2 plus cosine square of 2 theta over 3. This representation, of course, here, as you can see, is very complex. It has very different variations in patterns, and it's very difficult to do by hand. So for that, we need some technology. Some good technology to use can be graphers like Desmos. So for example, we can start with the elementary things like r equals 2, that immediately graph as a circle. And just let me show you how you do it from scratch. You simply put an expression and you say r equals 2. And this is going to even give me the chance of change in vary r. So for example, here we start with a circle of radius 2, but if you want to move, you can increase the value, and that's going to give you different circles according to whatever you want. If you're looking now for something that is in terms of r and theta, like what we saw earlier, then you can use like r equals 1 sine of theta, and of course you gotta move theta a particular angle. So here we're gonna move theta from 0 to pi. So notice this is the cardioid that we have from before, and you can use this to kind of guess how it's gonna behave in different places. So for example, if we go with 0 to pi half, you can see here that we're only checking for this part. If we do 0 to pi, then now we complete this entire run around up to pi, and then going by 3 pi over 2, we add a little bits that we have from before, and 2 pi is finally going to complete the whole thing. Okay, so this is a good way of knowing how the shapes are going to behave, at least with technology. And this is something that is very unlikely that you'll have to do by hand by yourself. So yeah, it's always good to learn how to do it with technology. Same thing with r equals cosine of theta. And notice that if you go even further, like for example here 0 to, I can go with 0 to pi half to see what happens, and you can see that it's producing this. In 0, obviously this is going to be 2, so it starts from 2 and it starts reducing back to 1. Then from 0 to pi, we notice that from pi half to pi is reducing from 1 to 0. And then if you go 3 pi half, then again it starts increasing from 0 to 1 in terms of radius. And then finally, if you do 2 pi, then you complete the full cardioid in this direction, and it produces this. If you increase the numbers of turnaround on the circle, for example 0 to 4 pi, it's going to produce you the same thing, because it's just going to repeat the pattern of what it's doing. Okay. Now if we do some of these complex ones that we have over here, so for example r equals sine cube of 2.5 theta plus cosine cube of 2.5 theta. Oops. Erase what I was doing. Okay. Anyway, typing this is something that is getting a little bit annoying here. So I'll always end up erasing instead of leaving it be. Okay. So this is here is not producing the variation. So maybe if I just write D here. Okay. Only sine square. Otherwise use parentheses. Okay, this is not supporting this. So let me see if I just write this in the correct way. Okay, I have some issues with this. Let me try and see if I can do instead the second one. I gotta figure out why it's not actually letting me use. Yeah. Now it's gonna probably produce what I was expecting. And now it leads me, it actually lets me do. So for example, I can go 0 to pi. And 0 to pi is only going to give me this piece. 0 to pi half. You can see how it starts drawing the pieces. I can go to 3 pi half and it's going to go for this. And when I go to 2 pi, it does this. And so notice that even getting to 2 pi is not enough to complete this graph. It probably got to do with the fact that this here is just giving me more of more splits. So let me see if I do 4 pi. 4 pi, it gets more around, but it also doesn't finish the curve. So now I gotta get up to 6 pi to be able to complete the whole curve that I have over here. So sometimes it's very important to determine what is the domain where theta is moving to be able to complete these graphs. Okay, one example more will be this graph of cosine of theta, a theta over 5, and this would be a cosine of So this looks like this, but obviously I gotta determine the domain. So the curve is gonna repeat itself after 5 rotations, And this is something that is almost given immediately to me here. You can see 0 to 10 pi, which is 5 0 to pi rotations. But if you prefer, you can start drawing it piece by piece just to see how much it covers. So pi half goes to here, pi goes to here, 2 pi goes to here, 4 pi goes to here, 6 pi goes to here, but it doesn't complete the pattern. 8 pi goes to here, and finally at 10 pi it completes everything that it needs to be full. So the resulting graph here is showing 60 loop, so it's going twice over this. So now you see the advantages of course doing this multiple times. 16 loop will be like go 32. So this would be giving me this. Okay. So this is how you will do this with technology. Now, after that introduction, we're gonna see some more examples on the practice videos of how you can actually play with this and work a little bit in the representation of some of these angles. And later, the important part is that we're gonna be doing calculus with this type of curve. So the representation is one thing, but we always wanna move from the representation to actually doing calculus. As you can see, we can really use technology to just find the representation of each what this functions is doing. So that is the end of the introduction to 10.3.